Hi, I'm Yaswanth. I'm graduated from VR Siddhartha Engineering College in the stream of Computer Science and Engineering. So I'm here to present our paper. So the title of our paper is Facial Microexpression Classification through an Optimized Convolutional Neural Network using Genetic Algorithm. So coming to the abstract, computer vision facilitates machines to interpret the visual world using various computer-aided detection-based techniques. It plays a crucial role in microexpression autoclassification. A microexpression is a pre-facial movement which reveals a genuine emotion that a person tries to conceal. It usually lasts for a short duration and is imperceptible with normal listening. To reveal people's genuine emotions, an automatic microexpression screening using convolutional neural network is in great need. Traditional methods for microexpression recognition suffer from low classification accuracy due to inadequate CNN hyperparameter selection. The proposed approach addresses these challenges by using an optimized CNN with adequate learning rate, batch size, epochs, and dropout rate. The real-coded genetic algorithm has been employed for hyperparameter optimization. In the experimentation, features are extracted from the onset and epochs frames of microexpression video clips of CASME II dataset, the CASME II dataset. The proposed model's performance is measured using various metrics, including accuracy, precision, and recall. The proposed approach's performance is then compared with the optimized CNN using random search algorithm. The empirical investigation of the existing CNN-based methods has proven the efficacy of the proposed model. Coming to the introduction of the paper, facial microexpressions are vital in human interactions for nonverbal communication of emotions and intentions. Microexpressions are involuntary, subtle, and fleeting facial expressions that reveal the genuine emotion of an individual. Common applications of recognizing microexpressions include deception detection in various scenarios, such as investigations, understanding patients' emotion to improve medical care, evaluating interviewee loyalty, and enhancing customer service interactions. Automated facial microexpression recognition presents a significant deep learning challenge due to its complexity and multidimensional nature. Prior studies have addressed this challenge through the integration of spatial and temporal features for effective microexpression classification. These methods consider both visual cues such as facial appearance and muscle movement, as well as motion-related factors such as speed and duration, but they often overlook the intricacies, the challenges associated with processing complete video sequences. Usually, CAD-based MER processes comprises several crucial steps, including data preprocessing, pertinent feature extraction, and the application of emotion classification techniques. Our proposed method employs a CNN architecture where onset and epoch frames of microexpression video clips are stacked along input channels to enhance the spatial detail and sensitivity to rapid facial movements, and hyperparameters are optimized using GA, improving the convergence towards optimal settings and reducing the computational complexity. The model's performance is evaluated on CASME2 dataset. And also we added many related works which would help us for doing this project. Coming to the method. In this approach, a CNN architecture has been proposed with a GA-based optimized hyperparameters. We found that the utilization of CNN for image classification tasks coupled with hyperparameter tuning using GA correlates with enhanced accuracy. CNNs excel in automatically learning hierarchical representations of features from raw image data, effectively capturing local patterns and features through convolution pooling layers. Genetic algorithms automate the tedious process of hyperparameter optimization by iteratively evolving candidate solutions, efficiently searching the complex hyperparameter space of CNN to maximize the performance. The combined approach not only leverages the feature extraction capabilities of CNN, but also optimizes the hyperparameters as learning rates, batch size, filter configuration, leading to improved accuracy and generalization on image classification tasks. The proposed method in the study tend to have an inordinately higher proportion of accuracy improvements as compared to the traditional approaches. By integrating CNN with GA-driven hyperparameter tuning, researchers can streamline model development, elevate manual effort, and achieve superior performance in image classification. So coming to the latest step in our proposed method, pre-processing. So the dataset in our study is widely recognized CASME II dataset, which serves as a benchmark for spontaneous microexpression analysis, providing a collection of 255 spontaneous microexpression sequences from 26 participants. And it covers a range of 7 microexpressions including happiness, surprise, disgust, repression, fear, sadness, and others. And the subsequent subphases, pre-processing the CNN model and its optimization per MER. The pre-processing pipeline involves extracting the onset and epochs frames from the microexpression sequence from each microexpression sequence, and this is followed by image grayscale conversion and contrast enhancement using HE approach. Then both the epochs and onset frames are stacked along the CNN input channels for expressions. Pattern learning. Subsequently, the data augmentation is employed to address the data size limitation. Various transformations are used to augment the minority class, stacked onset, and epochs frames. And then coming to the proposed CNN model. So the proposed CNN model architecture has 3 pairs of convolution and max pooling layers, as we depicted in the paper. In figure 1, convolution layers are particularly effective at detecting patterns and features in the image, while pooling layers help to reduce the spatial dimensionality of the output. And we use the relative activation function. And then coming to the optimization of the CNN model. Hyperparameter optimization is widely employed approach to enhance CNN prediction accuracy. Specifically in this optimization, 4 key parameters: the learning rate, batch size, dropout rate, and number of epochs have been considered. The choice has been made based on the results obtained from existing optimization-based CNN experiments with significant outcomes. In the experimentation, we have empirically investigated the performance of GA and random search optimization methods in MER. The real coded genetic algorithm. RCGA is optimization technique based on principles of natural selection and genetics. It uses real-valued representation for individuals in population. It allows more flexibility in handling of continuous variables during evolution. It achieves an optimal solution by evolving the individual population through selection, mating, crossover, and mutation process. In the study, the initial chromosome population is selectively generated. So it is done through testing various hyperparameter combinations, creating a diverse and promising starting point for the GA optimization. This approach ensures a faster GA convergence with relatively suitable population. And in table 2, we gave an example of chromosomes encoded with the values for the 4 hyperparameters which were chosen. And also we provided a clear algorithm for the genetic algorithm that we employed for optimizing the hyperparameters. So this stands out to be our main algorithm. For this, in the mutation, we use 2 kinds of mutation. One is the Gaussian mutation and the uniform mutation. And coming to the other techniques which we have also used to compare its performance. Random search. So random search is a popular approach for hyperparameter tuning which randomly samples hyperparameters from a defined search space. So in the study, a random search has been used to determine a set of optimal CNN parameters. Coming to the results and discussion. This study investigated a comparative study between the performance of 2 optimization techniques employed in our research and compared our work with state-of-art methods in the field of microexpression classification. Through this analysis, we aim to gain insights into the efficacy of optimization approach and its competitiveness in the current landscape of microexpression classification methodologies. And additionally, we sought to identify the potential areas for improvement and future research direction within the domain. And the optimal hyperparameters, the RCGA, the real coded genetic algorithm, and random search have been employed starting with the initial population of 5 potential chromosomes. The individuals with higher accuracy after running for 5 generations has been considered for optimal choice. The results were depicted in Table 3. The optimal hyperparameters determined by proposed RCGA and random search are utilized in the construction of two separate CNN models. Further, a CNN model is built without any hyperparameter tuning for the baseline evaluation. And we also added a table which depicts the optimal hyperparameters determined by RCGA and random search. In the following order: learning rate, batch size, dropout rate, number of epochs. The optimal hyperparameters determined by CNN optimized GA is 0.0006, 17, 0.29, 52. And for random search optimized CNN, the parameters are 0.001, 64, 0.3, and 60. The classification performance. The performance of the three CNN models is evaluated on the CASME II dataset using various metrics including accuracy, precision, recall, F1 score, and UAR. And by employing multiple evaluation metrics, we aim to gain a comprehensive understanding of the strengths and weaknesses of each model in accurately classifying microexpressions within a given dataset. Table 4 presents a comparison of performance of the three models. So, the accuracy for standard CNN is 0.76, while when it is optimized with RCGA, it is 0.8924, which is 89.24%. And when optimized with random search, it is 86.0%. So the evaluation has revealed significant improvements in performance of the proposed RCGA optimized CNN framework. More precisely, it exhibited 12.9% higher classification accuracy when compared to non-optimized CNN, and 3.22 higher accuracy when compared with random search optimization CNN. The proposed framework achieved highest QAR with a value of 90.93%, surpassing the performance of other evaluated models. Similar trends were observed across the other metrics as well. The results highlight the superiority of the performance of the proposed framework. The variation of the prediction accuracies for all three models used in experiments are depicted in Figure 3. We also depicted a graph which signifies the performance of the three different models: standard CNN, CNN optimized with RCGA, and CNN optimized with random search algorithm. The standard CNN model initially achieves an accuracy of 30%, which gradually stabilizes at 76% approximately after 35 epochs. In contrast, the CNN with random search exhibits more fluctuations, with accuracy ranging between 65 to 70 during the first 15 to 25 epochs, before reaching the peak accuracy of 86 around 60 epoch. Notably, the CNN optimized with RCGA demonstrates fewer fluctuations compared to the random search optimization, starting at 28% accuracy and increased to approximately 18% over the course of 52 epochs. The comparison highlights the effectiveness of optimization techniques such as RCGA in enhancing the performance and stability of CNN models, as evidenced by superiority in accuracy achieved with the similar epoch range compared to the standard CNN and random search optimized CNN. The corresponding confusion matrices obtained by optimizing hyperparameters of CNN through random search and RCGA are also depicted in the paper. Upon comparison, the second confusion matrix demonstrates a more balanced distribution of misclassifications across classes compared to the first matrix. Here, the second matrix corresponds to the RCGA CNN. Comparative evaluation. Subsequently, a comparison has been conducted between the proposed RCGA optimization CNN model and the existing microexpression recognition baselines that use CNN architecture and deep feature to evaluate the overall performance of the proposed model. and the comparison is depicted in Table 5 in the paper. The proposed method may benefit from RCGA optimization without negatively affecting the overall performance of the CNN model. The proposed model secures 3.24% and 5.02% improvement in the recognition accuracy and F1 score over the D3 DCANN framework, and secures approximately 7% and 14% improvement in recognition accuracy and F1 score over the SE CASME II plus EVM framework on CASME2 dataset. This shows considerable improvements in the performance over the other stage of art methods for microexpression classification. We've also provided a comparison chart of the proposed approach with state-of-art methods in the paper in Table 5. Coming to the conclusion. In this study, we proposed a novel optimized RCGA CNN model for spontaneous spatial microexpression classification, achieving the remarkable accuracy of 80.24%. Our research shows that the proposed model, optimized RCGA CNN, is more resilient with traditional CNN methods, without hyperparameter optimization. Recent observations indicate that dataset imbalance significantly affects microexpression classification accuracy. Our results offer definitive proof that addressing dataset imbalance through data augmentation techniques leads to improved classification accuracy rather than being caused by increased quantities of training data alone. The findings achieved not only advance the state-of-art in microexpression recognition, but also hold practical implications for real-world applications, requiring accurate and reliable emotion detection. Future research may look into integrating generative adversarial networks, GANs, and exploring advanced techniques like attention mechanisms and transfer learning to further enhance the robustness and versatility of the microexpression recognition systems, paving the way for broader application in security psychology, human-computer interaction, emotion recognition technology. Additionally, considering other datasets beyond CASME2 and addressing the handling of real-time data are important areas for future scope and development. Acknowledgement: the CASME2 dataset used in the study was given by CASME series database managers. We would like to express our deep and sincere gratitude to Gently for providing the corresponding information and the dataset. This research did not receive any specific grant from funding agencies in the public, commercial, or non-for-profit sectors. The authors do not have conflicts of interest with anyone. We've also added the references and a list of authors. And this is the presentation of our paper. Thank you.